And so when you're dealing with oblique or not triangles that are non-right triangles, there's a couple special cases that you can use, and they have specific equations or formulas or relationships that can be used for those. So let's take a look at one instance of this. Okay, so if we take triangle ABC here, and we call the side opposite angle A, the side opposite angle B, and the side opposite angle C, lowercase c. And this will be how it's normally labeled. Okay, so if you take any non-right triangle, you can break this triangle into two right triangles. So Jacob, that answers your question as far as can trig ratios apply. They can apply if you create an altitude. Because what we've done by drawing in this altitude is we've created a right triangle on the left, and we've created a second right triangle on the right. And together these form that whole triangle. So you can break it down into right triangles. But when I break this down and talk about these, let's call that altitude h for the height of the triangle. Okay. Instead of having to break it down every time and then relate all these different pieces, there's a specific formula we can derive by doing it just this one time. So let's derive this, and then I'll show you how it applies. Okay, so if we look at the triangle on the left, we have this angle A. With respect to angle A, the pieces labeled are the opposite side and the hypotenuse. Well, which trig ratio relates opposite and hypotenuse? It's the sine, right? So we could make the statement that the sine of A is equal to opposite h over hypotenuse b. Okay, well, in the triangle on the right, we can set it up in a very similar fashion. We have an angle B. With respect to that angle, we have an opposite side labeled, and we have an hypotenuse labeled. So once again, opposite and hypotenuse refer to which trig ratio? Sine. So we know that the sine of B is equal to h over the hypotenuse A. Well, when we look at these two equations, what do they have in common? They both have h in common. So let's solve each of them for h. So on this first one, if we just multiply both sides by b, we can isolate our h. And in this second one, if we multiply both sides by a, again, we can isolate our h. So we have two different values for h. Well, we've already talked in the section on the logic. If two things are equal to the same thing, then they are what? Equal to each other. So by transitive property, we could make the claim that b times the sine of a is equal to a times the sine of b. And if we manipulate this one final time, just to get the pieces with the same letter on the same side of the equation, we can divide both sides by b. That moves this b over to the right. We can also divide both sides by a. That moves this a over to the left. And we get what's called the law of sines. And that states that the sine of a over a is equal to the sine of b over b. And this generalizes into another relationship, sine of c over c. It doesn't matter how you set these up. You're always going to be able to set up this law of sines proportion. And so rather than going through and drawing in your altitude every time and then setting this up, you can simply go straight to the law of sines. So let me just rewrite this. The law of sines states that the sine of A over the side opposite it is equal to the sine of angle B over the side opposite it, and that's equal to the sine of C over the side opposite it. Now, you'll only ever need to use a pair of these relationships. You'll never do all three in the same calculation. Okay, but you can flip them. Ratios are the same whether they're done numerator over denominator or denominator over numerator. So we could also flip this, A over the sine of A equal B over the sine of B equals C over the sine of C. So those are equivalent. It doesn't matter which one you choose, it'll lead you to the right answer. When I suggest that you use one way or another, my suggestion is use whichever form puts your unknown in the numerator of your fraction. It just makes it easier to calculate. Okay, so the law of sines can be used with oblique triangles. Again, oblique just means non-right. If you have a right triangle, there's going to be a handful of you who will use law of sines for right triangles. It's not necessary to do that. It's not going to be wrong, but using the law of sines for right triangles is a waste of time because the trig ratios, SOHCAHTOA, already allow you to do that. So for right triangles, just use SOHCAHTOA. For non-right triangles, you can look for one of these patterns. And the way that you determine whether you use law of sines or whether you use the relationship we're going to talk about tomorrow is based on the pattern of information provided. So law of sines is going to be used for any pattern that involves two angles, so ASA or AAS, and it's also going to be used for SSA. So if that's the set of information I give you, so if I give you two sides and the non-included angle, you can use law of sines to find the remaining pieces of information. If I give you any two angles and then a side, whether it's between the two angles or opposite one of them, you'll use law of sines.